In this talk, I will explain what analogy making is, why it plays an important role in software engineering, and how we can design automated tools that reason about software using analogies. An analogy is when you understand one thing as essentially the same as something else. Analogies are extremely common in everyday speech and writing. For example, here's a news headline describing the recent Bay Area air quality by analogy to nuclear winter. Of course, the Bay Area isn't literally experiencing a nuclear winter, but readers can very quickly get a pretty good understanding of what's meant by this comparison. Here's another headline, which is really filled with analogies. For example, comparing the pulsing of a star to a musical tune. The astronomers aren't literally listening to these stars like music, but the analogy communicates their interest in the patterns very effectively. Finally, analogy making is also very common in technical discussions. Here's a paper on Newtonian program analysis, which adapts Newton's root-finding method to find fixed points of programs. Their algorithm is not exactly the same as Newton's method, which worked for polynomials on the real line, but for anyone familiar with both Newton's method and program analysis, these three words communicate very effectively the core idea of the paper. In fact, analogies are used extensively in software engineering as well. One place this comes up often is when programmers understand one piece of code as essentially the same as another. For example, suppose you're the maintainer of the bash shell and wrote the code here on the left that manages built-in shell functions. Next, imagine you wanted to make a bug fix on the source code of a different shell, the fish shell shown on the right. Before fixing the source code on the right, you would have to understand it. One common way to approach this is to recognize that some functions and data structures in the fish source code play essentially the same role as the corresponding ones in the bash source code. For example, a data structure to store built-in functions or a function to look up a built-in. This example highlights how we rarely understand code in a vacuum from first principles, but instead we're usually looking to form analogies between higher-level patterns and concepts familiar to us from software we already understand. We also make analogies between code transformations. For example, here we have two before and after code snippets, where we've changed calls to some method gemLarge to call a different method gemSkinny, perhaps as an optimization. We can form an analogy between these transformations, realizing that both of them do essentially the same thing. Change a method calling gemLarge into one calling gemSkinny. We might also realize some similarities in the surrounding code, implying, for example, that we only want to do this when the arguments are of a certain size. Once this analogy is made and we have an understanding of the core transformation both of these are examples of, we can apply the transformation to a new piece of code, such as the one here, and infer what the optimized version using gemSkinny would look like. So what we've seen is that it's common for humans to reason about code using analogies. The question we ask is whether computers can do the same thing. In fact, they can. This has been studied by cognitive scientists since the 60s, and primarily this research looks at problems in very small microdomains that abstract away much of the complexity of everyday conversation, or in our case, source code. Let's look at one popular microdomain, where the goal is to identify the essential similarity between short strings of letters. For example, consider the strings ABC and EFG. We can see that both strings can be described as having successive letters as you go rightward. We can describe this essential similarity in a first-order logic notation like so, where we say that any two letters in the string are successors if they're next to each other. If we zoom out a bit, what we can see is that this process of identifying essential similarities is actually a process of abstraction. From two examples, we've identified a core that they both share. So the first takeaway we get from this microdomain is that we can think of analogy making as abstraction. However, letter strings are not always so simple. If we consider comparing these strings, for example, it's not clear how to describe their fundamental similarity in any kind of reasonable first-order logic notation. With that said, most people can draw the essential similarity in a diagram like this one. In this drawing, we characterize these strings as having groups of letters, where within each group the letters are all the same, and between the groups some relation R holds. In the first letter string, for example, this R might be that the groups are successive letters and going rightward, while in the other string they might be successive letters going leftward. So the second takeaway we get from this example is that we really need a flexible representation to describe such commonalities. On top of that, the final takeaway is that we'll often need to revise our representation of the objects in order to compare them. For example, viewing AABBC as 3 groups of letters instead of just 6 independent letters. With these lessons in mind, we designed the Sifter framework and algorithm for making analogies on program source code, documentation, and other associated artifacts. Sifter combines a novel data structure for representing knowledge about these objects with expressive update rules that make analogies and inferences involving that knowledge. In Sifter, we represent knowledge as triplet structures, which is a new data structure introduced in our paper. Formally, triplet structures are composed of a set of nodes and a set of facts, where the facts are just triplets of those nodes. We can represent triplet structures as a graph by drawing each fact as a labeled edge in the graph. For example, this triplet structure has 9 nodes. 5 of the nodes represent people, like Homer and Lisa, while 2 of them represent more general concepts, like the parents or children in a family, and 2 of them represent facts about the other nodes. In particular, node F1 claims that Homer and Marge are the parents of a family, with Bart and Lisa being the children. Meanwhile, F2 claims that Abe is the parent of Homer, the child in that family. Triplet structures have a number of benefits. They allow a uniform representation of facts that doesn't require special handling for different arities or order of functions. They can effectively represent partial facts that may be filled in more completely later during an inference process. And finally, they can be efficiently implemented to enable fast querying and modification. We can represent analogies in triplet structures as a form of abstraction or anti-unification. On the left here, we have a triplet structure that represents 2 letter strings, AB and BC. Here, x1 is corresponding to this A, this y1 is corresponding to this B, and so forth. On the right, we show how we can represent the essential similarity between these 2 strings. Namely, we introduce 2 new nodes, this alpha1 and alpha2, which represent essentially abstract letters, and we add facts saying that AB and BC are both instances of those more abstract letters. Finally, we lift any common facts about the concrete nodes into the abstract, such as stating that the first abstract letter should be an alphabetical predecessor of the second abstract letter. This idea is described in much more detail in the associated paper. Comparing AB and BC is a relatively small task that's mostly syntactic. In general, we view analogy making as having 3 main interoperating components. First, we do raw perception to add syntactic information about the inputs into the system. In a letter string scenario, this would be just the letters in their relevant positions, while in a software source code, this may involve adding nodes corresponding to tokens in a file, for example. The next component implies semantic rewriting, which exposes some semantics of the problem in the syntactic representation itself. For example, we might modify our representation of the 2 letter strings to group together different substrings. The final component performs abstraction, pairing up components from the second step that play similar roles. Importantly, there's not a linear progression through these components. Instead, all 3 need to interact during the process. In source code, for example, we might want to start by only trying to make analogies on a small subset of the code, then iteratively adding more files to our workspace as we make stronger and stronger analogies. We may also find that 2 pieces of code that we think should be the same don't appear syntactically similar. So component 3 might request the help of component 2 to do inlining, desugaring, or even rigorously analyzing code to help identify more fundamental similarities. These last 2 components, semantic rewriting and syntactic abstraction, rely heavily on iteratively modifying the structure. For Sifter, we've introduced a domain-specific language that makes writing such structure updating programs easy. Here I've shown 2 examples of these rules. They look like triplet structures, and you can actually express them reflectively in the structure itself. At a high level, these rules define a pattern to be searched for in the structure, followed by some manipulations to change the structure when there's a match found to that pattern. These are described in much more detail in our paper. So far, I've introduced the Sifter program for making analogies on program source code. It combines a new form of knowledge representation with a domain-specific language for update rules that operate on that representation. Because Sifter's triplet structure representation is so general, we can use it to encode all kinds of information about code, documentation, and surrounding context. For example, here I've shown a representation of a small code file after a simple tokenization pass. Depending on the level of semantics you know about your language, you can annotate the code with all kinds of information, ranging from syntactic rules of different tokens to the type of semantic invariance you would get from a program analyzer. This is again described in much more detail in our paper. I'll now describe 3 case study uses of the current Sifter implementation before finishing the talk describing the next frontier of challenges in this domain. The first thing we can do with Sifter is comparative program understanding. Given 2 code bases, such as the snippet shown here, Sifter can identify when some component of one code base plays essentially the same role as a component of the other code base. For example, here Sifter has inferred that the cd built-in function on the left might play the same role as the built-in cd function on the right. Sifter can then build out its analogy, identifying even more similarities between parts of the code bases. These automatically identified correspondences can then be used to help developers get up to speed on a new code base by referencing code that they already understand. The second application we explore for Sifter is program transformation learning. Given two example pairs of programs before and after some transformation, Sifter can identify a general representation of the transformation itself. Importantly, because Sifter's input is described as a generic triplet structure, we can include arbitrary semantic information in our analogy. For example, we may run a program analysis tool to identify that both of these snippets have an invariant relating the last two parameters of the call to gem large. Sifter can use this information in its analogy. For example, it may warn against generalizing this transformation to code where a corresponding invariant does not hold. Once Sifter has made its analogy, we can ask it to complete the analogy given a new code snippet, such as this one on the left. In this case, Sifter identifies that the corresponding invariant does indeed hold in this code, and so recommends applying the learned transformation, producing the optimized code on the right that correctly replaces the call to gem large with the call to gem skinny. The final case study we explored in our paper was that of API migration. We consider a library called CameraLib, which was recently updated from version 1 to version 2. Version 2 is similar to the old version, except a parameter has been dropped and all of the error codes have been updated. We suppose we have a few examples of code migration, meaning pairs of code before and after moving to version 2 of the library. We then take both the old documentation, new documentation, and two examples of migrated code, as well as a different code snippet that's still using the old version of the library. We provide all of this to Sifter, which then makes an analogy, essentially identifying what it means to migrate code to use the new library version. From here, Sifter can correctly synthesize the migrated code for this snippet, removing the extra argument and updating the return value. One really important thing to notice here is that neither of the two examples we gave Sifter involved an error value of -6. Instead, Sifter had to learn as part of its analogy to actually look up the new error value in the documentation. So this example really highlights how having one tool that can synthesize information from both natural language documentation and source code examples can be more powerful than just source code alone. Now that we've discussed what the current implementation of Sifter can do, let's look at a few challenge problems in this area of analogy making. Suppose you prove that this function, which computes the max of a list, is correct. Let's suppose you're given a different function, which is essentially the same as this, except for some slight differences. For example, this function on the right computes the min of a list. An effective analogy maker should be able to essentially lift the proof from the max function to construct a corresponding proof that the analogous min function is correct as well. A somewhat fuzzier way we use analogies is to infer the behavior of operations. For example, in this code snippet on line 2, we used the plus operator to perform string concatenation, a common operation in many programming languages. What's less common is a minus operation on strings. However, although almost no major languages support this operation, most people can probably guess what the intended value of current dir minus home is in this code. The key way we approach this question is to reason by analogy. Specifically, we know that regular arithmetic subtraction undoes addition, so we would expect string subtraction to undo concatenation. So here we would expect the subtraction on the third line to undo the addition on the second line, giving us back just hello world. Although this might seem like a silly example, software engineers reason by analogy to guess at the names and behaviors of library methods all the time, especially when first learning a new language or library. In this way, automated analogy making can help more effectively infer the specifications for library methods that are commonly treated as wildcards in many program analysis tools. Finally, in a much broader sense, programmers make analogies to physical and mental models of their software. These 5 lines of code, for example, aren't literally doing much more than just controlling some bits in the computer's memory. But in order to give meaning and interpretation for us as software engineers, we embody them with rich ideas about killing and aborting workers, cleaning up files, and so forth. This kind of mentality of treating parts of programs as things that can be interacted with in an almost physical sense is really close to the heart of object-oriented programming, and our automated tools would do well to really understand and take advantage of this fact. In this talk and the accompanying paper, we describe the role of analogy making in software engineering. We proposed a new algorithm, Sifter, for making analogies involving software. We demonstrated the use of Sifter on 3 example tasks, and we ended with a number of challenge problems to motivate future research in analogy making for software engineering. The code for this paper is available on GitHub at the link shown.